In this video, we're going to derive a general formula for finding the force between two current carrying wires that are parallel. And we're going to motivate this with some specific calculations first. That's in A and B. And then we're going to get the general formula in part C. So the basic qualitative idea is that if I want to find the force between two wires, I look at the field generated by one wire. That's going to wrap around that wire according to the Ampere's law right-hand rule. And then I look at what kind of force per unit length that exerts on the second wire. So we're smashing two ideas together here. In part A, I'm asked to find the field at the bottom wire generated by the top wire, and then I want to draw the direction of the force that creates on the bottom wire. So I put my thumb in the direction of the current in the top wire and wrap the fingers of my right hand around, and I find that the field generated by that top wire would be coming out of the page above that wire. That's not the region we're interested in, but I'm doing it for completeness. And that field is diving into the page below that wire. Then I look at the current in the bottom wire, and I use the Lorentz force right-hand rule. And my favorite version of this is to put my fingers in the direction of the current and then sweep out to the direction of the magnetic field. And when I do that, my thumb points in the direction of the magnetic force, and that turns out to be downward. I'll call that FB. Now you could repeat this same process using the bottom wire as the source of the magnetic field and the top wire experiencing a force due to that magnetic field. But why not just use Newton's third law? If the top wire is pushing down on the bottom wire, then the bottom wire must be pushing up on the top wire. In other words, the force between these two wires is repulsive. In part B, I want to get quantitative and find the force per unit length on the bottom wire. So what I'm going to do is find the magnitude of the field first. I'm just going to keep these ideas separate, and we'll save the general formula for part C. So I'm going to start by finding the magnitude of B generated by that top wire, and we use the formula B equals mu naught I over 2 pi r, and we're going to plug in. Remember, r is the distance from the wire generating the field, so that's 0.15 meters. And I get 4.4 times 10 to the negative 7 Tesla. Then I move to my force per unit length for the wire that feels the field, and that's given by I, the current in that wire, times the magnitude of the field that it's feeling, times the sine of theta, where theta is the angle between the direction of the current and the direction of the magnetic field. Well, this current is perpendicular to the magnetic field, and that's always going to be true when the wires are parallel. That means theta is 90 degrees and the sine of theta is 1. And this will even be true when we do the general derivation down here. We're talking about parallel wires, so that angle is always going to be 90. So to 3 sig figs, I get 1.45 times 10 to the negative 7 newtons per meter of wire. So now it becomes clear why this is so difficult to get to work in the lab. We're talking about incredibly small forces here. You'd have to crank the current up very high to get a significant effect. Now let's get the general formula. So there's not much to be done here. I'm just going to write down the force per unit length on the bottom wire, and we're going to call that a current of I2, where the field it's feeling has been generated by the first wire, so we'll call that B1. And again, if the wires are parallel, then that current is perpendicular to the magnetic field, so the sine theta is out of the picture. And then I plug in the formula for the field generated by the top wire. That was mu naught I1, where I1 is the current in the first wire. And I arrive at a general formula for the force between two parallel wires. The only thing to add here is that we noticed that the force was repulsive if the currents were in the opposite directions. Well, if those currents are going in the same direction, that would just flip the force on this bottom wire because the current would be going the opposite direction for the right-hand rule. So that would be an upward force on the bottom wire, and by Newton's third law, downward force on the top wire. In other words, it becomes attractive if the currents are in the same direction. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.